Welcome to the Newton tutorial series. I'm Mike Cruz with AC-Tek, and in this tutorial I'm going to continue my discussion of viewing our simulation results in playback file mode. Specifically, we're going to talk about using the features in this plotting window. So the plotting window is used for viewing your simulation data in graphical form. There are a few different options that we can look at in here. We have tabs that allow you to plot tonnage, work, or triangle forces. So one thing to note that when we're plotting data in the plotting window, it's similar to when we're looking at wear or force summaries in the SMV window. The data, the tonnage and work and triangle force data is encoded in the playback file, and in order to get at that data we have to generate a plot and allow Newton to plot that data one frame at a time. So let's change our view, outer lines, and the tonnage tab. What the tonnage tab does, it allows you to view the tonnage flowing through a specific data box at different points of the simulation. So let's say we were curious what the input and output tonnage for this transfer chute are. Now, because this transfer chute is a one input, one output, of course the output tonnage has to match the input tonnage exactly, unless of course there's a buildup in blockage in the transfer chute. But if this chute was a little bit more complicated, maybe it had a flopper gate here and it could discharge one direction or the other, or maybe there was some other flow regulating device that split the flow between two different exit points, and maybe I wanted to measure the tonnage at both of those points, I could use these tonnage boxes. So the way we do this is we first set up our data box or our tonnage box that we're going to be looking at. So for this I'm going to look at the input tonnage right here and the output tonnage right here. So we'll set up a data box here. Turn on my UCS icon. Must be going from what, -1 to 1, -4 to -3.5, and 0 to 2. Okay, that's good enough. It doesn't matter how thick this tonnage box is. All that matters is that the particles enter the tonnage box. It has to have a thickness. I couldn't say -4 to -4. It has to be -4 to -3.9 or -3 or -3.5, whatever. So then for this section down here, let's go to a top view. We're going to use the blue one because I like blue. Okay, so x value -8 to -7, y position -1 to 2, z position -5 to -3. Okay, so now we have a tonnage box downstream and a tonnage box upstream from our transfer chute. We'll go ahead and generate a summary from, this file goes all the way to 40 seconds, but we don't want to generate that whole summary. We'll just go from 0 to 15. That should get us to steady state. And then we'll hit generate. I'll change my rendering mode to lines because that's going to render the quickest. And we can see that our data has started entering the input tonnage box. It's going to take a few seconds before the data gets to the output tonnage box, but in the meantime I'll discuss this moving average. So the moving average simply averages our tonnage data between the last 20, 50, 100, or 10 frames of the playback file. Because if we were just looking at the tonnage on a single frame-by-frame basis, we'd end up with a really jagged tonnage plot, and it'd be tough to see exactly what the tonnage was, because we don't really care about the tonnage at any single frame. We don't even care about the tonnage over 10 frames. We care about the tonnage over a long, several second period. So by averaging the data over 20 frames, I'm averaging the data over 0.2 seconds, because this is 0.01, 100 frames a second is what we're recording at. So by averaging over 20 frames, we're averaging over 1/5 of a second, which seems pretty reasonable. So now here our data has entered the output box. And as we would expect, the curve that we see for the output box is not rising as quickly as the input curve because we have a buildup taking place in this rock box. So until that rock box is completely built up and it looks like it's there already, we won't see this output match the input tonnage. If we go to a side view of this belt, let's get there, dang it. There, you can see, oh, somewhere right around here it looks like we've reached our steady state tonnage. So we'd expect that pretty soon we're going to be seeing this approach 2,000 tons per hour. And it's taking its sweet time getting there. Meanwhile, up in the top corner here, we're seeing a few counters, and basically this is saying this is the total number of clusters that have entered that input box and the total number of clusters that have entered the output box. This is the total mass of material that has entered this input box, and same for the output. And then here's the instantaneous tonnage in that box and the instantaneous tonnage in the output box. So these are the same values that are being plotted right here. This is just a current running total, you know, some curious data in case you wanted to see. And it looks like we are finally at steady state. So, if we hit stop, we can choose to, if we right click on the chart, we can choose to copy the image, the chart image, because perhaps I like the way that Newton does its charting. So I can just copy that image directly and paste it into Paint or Word or Excel, whatever you want to do. Alternatively, you can copy just the chart data, and it will copy the array of all 5 of these data boxes. It'll copy that data to an array, and you can paste that into Excel. So if I open up Excel, I can paste, and now we have tonnage 1, 2, 3, 4, and 5. Of course, going back to our plotting window, we only used tonnage 1 and 4. So if I scoot down to the end, we stopped this before we got all the way to 1500, didn't we? So if I scroll up, there's where we stopped. You can see we're using data box 1 and data box 4, and here's our time. So if I wanted, I could go ahead and insert a plot there, and there's that same plot. So the tonnage boxes are pretty simple, pretty self-explanatory. All you use it for is measuring the flow at different points in the simulation. And in order to use the tonnage box, you do not have to be saving the triangle work or the particle work or the triangle forces. In order to be looking at the work, the triangle work and triangle forces in these tabs, you have to save that triangle force data. But the tonnage is irrelevant, and that can be saved with any simulation that is recorded. So now going to our work tab, let's hide our particles because we don't care anything about the particles anymore. And let's also turn off those data boxes. So what we do with the work is, again, we have 5 different lines we can plot, and you select the layer that you want to plot and the work type. So I know that I want to look at the work on the back plate, and I want to look at the total abrasive wear. And for this line below it, let's look at the back plate again, but instead let's look at the instantaneous abrasive wear. So it's important to understand the relationship between these two values. The total abrasive wear, just for the sake of simplicity, let's also turn on the back plate so that we can see it in the rendering window. What's going on in the plotting window is separate from what's going on in the rendering window. So in order to look at the work on the backplate, I don't have to turn this on right here. It doesn't matter. But I just want to turn it on so that while this is plotting, we could also be looking at the wear being applied to the plate here. So let's make this so that the scale also matches. If I'm looking at the instantaneous abrasive wear, we want to be looking at triangle abrasion. And to get instantaneous, we'd probably want to be looking at, averaging over time and triangle area. So now let's do a wear summary from 5 to 15 and start that going. There we go. So the red line is our total abrasive wear, and that's the total wear that's being applied to the entire layer over time. So we're continually adding up the wear because our work units here are set to joules. We're continually adding up the wear on this whole layer. But the instantaneous abrasive wear is only plotting the work over the entire layer for a single frame. So that's why it's way, way, way down there. You can't even hardly see it anymore because it's so small. So if I just go from, let's just go from 5 to 6. Let's change our axis to go from 5 to 6. Oh, let's go from 5 to 7. Let's change this to go from 0 to 100. Okay, that's a little bit better. So just the very start of this curve, what you should note is that this red line is exactly equal to the sum of all the points along this green line. Because this is our instantaneous wear for the entire layer, and all we're doing to get the red line is adding up all of these wear values. And that's where that line is coming from. And that also means that we would expect that if I look over this entire time period, from 5 to 10, this green line is pretty constant. As soon as it gets to steady state, the amount of work being done is constant because we have the same amount of flow going over the same surface for, continuous period. And for that reason, we also see that the red line, once we get to steady state, the red line has a constant slope. Now what if I change these so that what if I change the work unit? So instead of looking at joules, we're looking at joules per second. What will happen now is this red line, rather than going upward, it will go up and reach a plateau. And then it will have a horizontal, it'll be a flat line because we're looking at the work per unit time. So it's just basically going to be the derivative of this line right here because we're dividing it by time. And the green line is going to change as well because while the green line before we were looking at the instantaneous work, the total instantaneous work, now we're going to be dividing that by the time interval. So because our time interval is 0.01 seconds, each of these little data points is going to be basically multiplied by 100 because each data point is going to be showing what would happen if the amount of work applied to this layer for that single frame, what if that amount of work was stretched over an entire second? So the relationship between these two lines is going to change. Let's go ahead and plot that with the joules per second. And now you'll notice that the green line is significantly higher than the red line. Because the green line says, well, again, what if we extended the amount of work that was done for an entire second? And the red line is taking the total work done and dividing by the elapsed time. So we see that as soon as our green line, our instantaneous work, has reached steady state, now our red line is also flattening out. And what if I wanted to look at, let's go back to work units in joules, and I want to look at the work on the receiving belt. Let's look at the total abrasive wear on the receiving belt. And let's go from 10 to 15 here. Well, now I see that the back plate is the red line, the receiving belt is the blue line, and clearly it looks like there's more wear on that back plate than there is on the receiving belt. Which seems reasonable because we know the material is going to be slowing down significantly on this wear plate. And because of the relatively shallow slope of the plate, the material is going to slow down quite a bit as it enters the receiving belt. So there won't be a whole lot of work done on the receiving belt. And of course, these lines are constant again, because once we reach steady state, we're doing the same amount of work over time. So if we switch to the triangle forces, let's look at the receiving belt forces. Let's get our same top view that we looked at in the last tutorial. We know that the material is going this way along the receiving belt. So let's plot the receiving belt parallel force. Let's do this one that's perpendicular, and this one will be the receiving belt parallel force. And we want to go from, let's go from 10 to 20. Now again, here we have that same filtering that we saw on the SMV window. We want to do some filtering because these forces are pretty transient and change pretty quickly. Now, there's an exponential filter on the SMV window that is not included in the plotting window, and we're going to change that so that the plotting window has the exponential. Because the exponential filter is, in my opinion, it's a better filter than the moving average filter. So now looking at this, the other thing we can do, let's go ahead and turn on the total layer force. So because we're looking at the perpendicular, we would expect that this value here should match what we see in the plot. And if this is 0 to 2000, then we're hovering right around 500 newtons, and that matches what we see here. Similarly, if we look at this bottom line, the parallel force, change that to parallel, well, right around negative 1800, and that's matching what we're seeing here as well. Something to note, when we're doing our moving average, the moving average is applied to the graph, but the moving average here and the moving average here, or the exponential filter, are not applied to this label. So this label will still be pretty transient up and down force. It does not get smoothed out like the rest of this data does. But if we set the moving average to 1, then we know that exactly what we see in this label is going to match exactly what we see in the plot. So what if I want to compare the parallel force on the receiving belt with, say, the parallel force on the backplate? Let's go ahead and plot that. And we see, well, what's going on here? Why is my purple line, why is my backplate line sitting at 0? And the reason is, I forgot to mention this in the previous tutorial, but the reason is because the backplate does not have a velocity. If you recall, we talked about how the parallel and perpendicular forces are determined relative to the velocity vector for the belt. But the backplate doesn't have a velocity vector. So how would we know what the parallel force is? Because we'd say, well, parallel to what? There's no vector. And because there's no vector, Newton simply records that force as being 0, so that you wouldn't happen to see some garbage numbers there that don't make sense. Now we're planning to change this so that what you could do is you could manually input a vector, and you could say, well, I want a vector that points in this direction, or rather points in this direction, and I'm going to call that my positive vector, up along the face of that backplate. Because then Newton would say, well, now I know what my vector is. Now I can calculate a parallel tangential force and a perpendicular tangential force, and I can plot those. But in the meantime, you can't record those forces because there's no velocity. Something you could do is if you gave this chute a very, very, very tiny velocity, say you gave it a 0.0001 velocity along the face, then the particles that impact that face wouldn't really be affected because the velocity is so tiny, but then there would be a vector that Newton can refer to, and Newton could record those forces with that vector. But again, we're going to change it so that you can just simply input the vector that it should use, and then it will record those forces. And as I mentioned with the tonnage plot, the same is true with the work and triangle forces. You can right click and you can copy the chart image or the chart data for both of these. And I believe that covers everything I wanted to discuss in these two tabs. So if there's anything else with these tabs that's not discussed in the manual or in these little help bubbles, then feel free to send us an email at info@actek.com. Thanks.